All right, so I want to give you a bit of an overview of the concept of resonance. It's a really important concept in chemistry, being able to essentially push electrons around on molecules and explain how ultimately a charge can be delocalized across a number of different atoms. This is something that a lot of people struggle with just in the beginning, but if you just push through with this and just look at the basic principles, once you get it, getting this foundation is going to help you immensely with understanding all of the reactions that occur in organic chemistry. It's a very foundational principle. It's going to teach you how to move electrons from one place to the next and the rules that are governed by that. Resonance is a very sort of dumbed down in a sense form of mechanism that we learn about. And essentially, the reason I say it's dumbed down is that resonance only involves pi bonds, all right, and lone pairs of electrons, electron lone pairs. So that simplifies exactly what resonance is to quite a degree. Now, when I explained this in class, I used this example over here. It's actually an allyl cation, but you don't need to know that. That's not important at the moment. It's an allyl cation, and what we did is, in order to make sure that we understood what was going on there, we drew out the Lewis structure of this. So if you haven't done this already, I suggest just pause the video, try and draw out the Lewis structure yourself, and then come back and see if you got it correct. All right, so the Lewis structure would look something like this: 4 carbons in a row, and there's a double bond between those 2 carbons over there. There is a hydrogen on this carbon, a hydrogen on this carbon, so they've all got 4 bonds, and hydrogens over there. And the positive carbon might be a bit tricky, but you should get to this quickly, and that is it must only have 2 hydrogens on it in order to be positively charged. So carbon just has 3 bonds to it. And so we have a positive charge on that carbon. And now what happens in resonance is that this positive charge is actually the result of an empty p orbital. If we looked at this whole molecule and we just took it from the side view, so I'm going to just draw, these are 4 carbons, we're looking at the side view like that, and we just looked at the p orbitals that are on those carbons. Now this one we have a p orbital, this one we have a p orbital, this we have the p orbital, this is the 1, 2, 3. This one has no p orbital. These are all just sp3 hybrid orbitals, so there's none over there, so we don't have to look at this too much. Now these 2 p orbitals over here form part of this pi bond that we have, all right, this double bond, and so the 2 electrons that are in those orbitals are shared together and they are connected like that. But what can happen in resonance is that those 2 electrons, instead of being shared between those 2 orbitals, they can shift across. Essentially what is happening is instead of them being bonded between those 2 orbitals, just shift across over here and get bonded between those 2 orbitals over there. So if we do it again, well, we don't need that one, what we get is now the electrons are in those 2 orbitals over there, so we now have a pi bond there, and this one is now empty, okay, with all these bonds between the atoms, sorry. Okay, so that's kind of what's happening in resonance, and essentially the net effect, so when we draw this one out, again, let's do it on the side, and remember when we do resonance, we have to use this arrow. This is the resonance arrow, and is only ever used to describe resonance. So only use it then. It's not an equilibrium arrow, all right? It's something separate. And so what has happened is the electrons have gone from there into those orbitals. In other words, the pi electrons here have moved across from there to there. And when we draw the Lewis structure out again, we do the 4, put all the atoms in. This is fairly tedious, and we need to be able to move away from this kind of writing out because it is very tedious and it's going to take too long to do this for all compounds. And now we see that the positive charge is sitting on this carbon here. And likewise, if the electrons can jump this way, when we get to this resonance form, the electrons can jump this way over there in order to go back towards this compound here. Now, of course, as I said, we need to move away from these types of structures. We must work with these sorts of structures over here, just the skeletal structures. And so how do we describe this same movement? Well, there's the double bond, and the arrow shows the movement of electrons. And it is critical, guys, that you understand that the arrow is showing, this curly arrow is showing movement of electrons. The electrons in this bond start here and end over here between the two atoms over here, the carbon atoms, where the sigma bond is, to form a new pi bond. And so the resonance form of this looks like this over here. All right. And likewise, this can bounce back. We've shown it already. Now we're showing on the skeletal structure. This happens like that. All right, so that was one example. I use this in class. Let me just show you another example. It's actually quite an important one because these are important intermediates in organic chemistry, although you yourselves are not going to have to deal with them, not in first year. But this over here is actually, if you want to Google it, it's a enolate. And it also exists in a resonance form. Now, in order to understand this, it's going to help you to make sure that you know how to draw this out in its Lewis structure. So again, I encourage you to just pause the video, try this for yourself. Please do. Just try it for yourself, and then look to see if you get the Lewis structure correct. All right. So Lewis structure is going to look like this. There are 3 carbons. It's a double bond between those 2 carbons. This one has 3 hydrogens on it. There's a single bond to the oxygen, and this must have hydrogens on it like that. And so the oxygen has a negative charge, and we should know how to fill in all the kind of lone pairs on the oxygen. It actually means it must have 3 lone pairs around it in order to have this negative charge like that, because oxygen would normally have 2 lone pairs, and the negative charge is contained in the 1 lone pair which is there. And so in order to do the resonance of this, how would this occur? How could a resonance form of this happen? Well, remember that in resonance, bring this back, it's all to do with the movement of pi bonds and lone pairs of electrons. And so if we look at this structure over here and we say, okay, can any electron move? Well, we have lone pairs here. If they're going to move, the only place they can move to is to this carbon over here. So if these had to move down to form a double bond here, a new pi bond onto this carbon, we would have a problem, all right? A seemingly big problem, because if they did that, we'd form a new bond, so then we'd have 1, 2, a new one, 3, 4, 5 bonds to carbon. That is a problem. We can't normally have that. However, because when we move those electrons in and we form a pi bond there, because this carbon has a pi orbital bonded to it, that pi bond, which is weaker, is able to break, and the electrons will end up on the carbon atom over there. And so the resonance structure of that, or form of this, I want you to actually pause the video here and try and draw out exactly what that looks like before I do it. This resonance form will look like this. C, 2 H's, lone pair of electrons now, because there's a minus charge there. Those are the electrons that moved out, and of course we've got the 3 hydrogens over there. All right, so now in order to go from there to there, you should try this yourself. All right, move the arrows. What happens is you go from there, and this will break and send the lone pair, this electrons in the pi orbital, out and onto the oxygen over there. So this is the Lewis structure drawing out, but actually we should be able to do it for these structures, the line structure is going to look like that. The movement of electrons onto the carbon, and so therefore we have a minus charge on this carbon over there. And moving back to complete it, so it goes back there, is that final resonance form. All right, now there are many different forms of this. There are many different examples of resonance that's going to occur, and I encourage you to just go and look at your textbook. And I'm now going to, in another video, I'm going to talk to you about some of the consequences of resonance.